So I think that I maybe oversold the title a little bit. I said, reliability best practices, but it's important to remember there is no such thing as best practice. They're only the lessons you learned from the things that you got wrong. So today I'm going to be sharing with you how we scaled our telemetry system by a factor of 10 over the past 3 years. Unfortunately, my co-presenter Terra could not make it. Please wish her well, but she is recovering from a health incident. So let's go ahead and recap the business case, because it doesn't make sense to build systems in the abstract. Can I get the timer started, please? Cheers. So it doesn't make sense to build fully abstract systems, right? Like, we're building systems for a purpose. So we have to make sure that the solutions we're building are fit for that exact purpose. So our purpose at Honeycomb is to analyze customer data. So we receive millions of data points per second from our customers about what their systems are doing. And we have to be able to give people real-time insight into what might have just happened like 5 or 10 seconds ago. They expect to see that data inside of our UI. But what do we really do? Well, I think the answers to what we really do is we try to simplify that confusion, but also our systems themselves can be a little bit confusing. So I'll try my best to walk you through how we try to design and architect our systems so that new engineers at Honeycomb can onboard successfully, and so that we can run our system with a minimum of toil and load. One thing really stuck with me when I joined Honeycomb about 4 years ago, which is Ben Harthorne, the first engineer at Honeycomb, the first hired employee at Honeycomb, said, Kafka is our beating heart. Like, please tread very carefully around it. Like, if you mess it up, it will cause disruptions all across the system. He didn't say, don't change it. But what he said was, be careful. And I think that that's really important to keep in mind when you're operating streaming systems, is that in a lot of cases, you are walking on a tightrope. There is not necessarily a lot of room to deviate. There's not necessarily a lot of slack and error margin in the system to allow for you to make these changes. These systems that are streaming are designed to be resilient and reliable kind of in their own bubbles. But as soon as you get outside of that safety margin, things can go very wrong very quickly. So as I mentioned at the start, we have scaled by a factor of 10 in 3 years. We've gone from roughly 250,000 events per second to over 2.5 million events per second. And we've also scaled from basically a relatively small number of humans using Honeycomb over the past 3 to 4 years to a much larger population of users, including one of our clients that has in the hundreds or thousands of engineers that are all onboarded into our product, and they are expecting to get those real-time analytics. The other trend that I'm going to point out is that this is not uniquely to us as a company. This is an overall trend in the ecosystem where more and more companies are relying on open standards like open telemetry to create these large volumes of debugging data that they can then use in order to better understand what's broken in my system, how do I fix it. And open telemetry is a very chatty thing. It produces a lot of data, and it's up to the backends to figure out how do you sift through that, how do you analyze it, how do you persist it without causing operational pain downstream or upstream. So I'm just going to gloss over this slide and say, yes, there's a lot of data ingest on the left. It flows through an API, and it flows through Kafka, right? Like, every single data point has to go through Kafka before it gets persisted and written out and queryable by our storage engine. That's the main point I want you to take away from this, is that the Kafka is the bottleneck. Everything flows through there. There is no alternative route around. This is where 100% of the stuff goes through. So today, this is what we're going to cover. We're going to talk about when should you use streaming services, when should you not use streaming services. Secondly, we'll talk about how to identify when you're hitting a scaling limit and what to do about it. And then third, we'll talk about how to really dig in, how to really understand how do I make the system operable if you do choose to operate your own Kafka cluster or your own streaming services. Yes, streaming is complicated. It's tricky to get right. But as you have an increasing volume of data, as you have more and more services that are depending upon that fire hose of data, especially if you're adopting something like event sourcing, you are going to find that streaming is a better, more supportable system than doing a request response and having each incoming event fan out into 5 events, because the data bus does handle it for you. It just takes a special kind of care and feeding that you don't get from working on pure request response services. So I'm Liz. I'm the field CTO at Honeycomb, and I've been with Honeycomb for 4 years. And my colleague Terra joined us about a year ago, and she is our staff platform engineer responsible for primarily for Kafka and streaming services at Honeycomb, but she's unable to join us today. So let's talk about the advantages of streaming and kind of how we got into using streaming without necessarily having that, oh my God, I have to adopt event sourcing mentality. So for us, the main thing that attracted us to using Apache Kafka was the idea of decoupling state from our systems. We knew that we wanted to be able to release to production every single hour, even more often than that if we could manage it, but we wanted to be able to release our services to production every single hour on the hour. And we wanted to be able to do so while achieving some fairly high reliability targets. We wanted to be able to have 99.99% of events sent to Honeycomb be successfully ingested quickly enough, right? You'll note that that's not 100%, right? There is some wiggle room. Service level objectives should not be 100%. But it is a number that is a fairly high reliability target. So we wanted to make sure that we could update the producer process that was basically ingesting the data from our clients, that we wanted to make sure that it was as stateless as possible. Sure, you might need to give it like a minute heads up of, hey, like I'm about to shut down so that you could drain it safely. But we didn't want to have this situation of our producers needing to keep all of this information around about here's all the work that I had in flight, and here's what I need to flush and restore from disk, right? Like that really hinders you if you're just trying to operate a system that operates on throughput. Getting the data from clients from the public internet, and then validating it and writing it out somewhere, right? If the place that you write it out to is Kafka, that means that you can kind of no longer have to think about things like raft protocols. You no longer have to think about Zookeeper. You don't have to think about how you keep locks. All of these things are handled for you by commodity off-the-shelf software, so that all you have to do is say, OK, I'm going to issue a produce request to Kafka. And as soon as it comes back and says, you've produced successfully, you can forget about all that information that you were storing in RAM, right? So it kind of enables you to say, I feel confident just doing rolling restarts of this service because it is fully stateless. The other interesting thing was that we wanted to make sure that on the receiving side of this, that there was some degree of redundancy, and that there was also some degree of hermeticness, right? That you could always create a snapshot of the data at any particular point in time and make sure that it was consistent and matched your peer. Because if someone is running a query against Honeycomb, they don't expect to, if they hit the run button twice on the same time range, they don't expect to get different results. They expect to get the same results, right? It would be very weird if we went from telling you, OK, there were 5,000 errors during this time window to, oh, there were only 4,500, right? What happened to those other 500 errors, right? We have to be consistent. And sure, one way of achieving consistency is to only run one copy of the thing. That gives you consistency. That does not give you availability, right? The CAP theorem is a real thing, right? So we want consistency. We want availability. So how do we do that? The way that we do that is everything that makes it into Kafka is ordered, right? It's an ordered log. And that was really important to us because that meant that if we always replayed the ordered log, we would always get the same output, right? So that enabled us to keep both of the copies of one shard of data consistent with each other. And that way we could make sure that we were always able to recover from failure conditions, that we're able to provision, maybe not even 2 copies, but maybe we're running an experiment and we want to tee off the data and tap the data and run a 3rd copy, right? So having that record of truth live with Kafka and having everyone who's worked on Kafka and done chaos engineering on Kafka and engineered it and found bugs and fixed it over the years, we didn't have to reinvent that wheel. It turns out that when you are a startup or even when you're a mature company, you only get a finite number of innovation tokens. You only get a set number of things that are like, I want to build my own, right? And I'm going to incur a bunch of effort trying to differentiate. So to us, it did not make sense to do kind of this and differentiated heavy lifting and build it all ourselves. We would much rather have just used a off-the-shelf product. Today, we might have chosen to go with something different, like Apache Pulsar, right? We might have chosen to use AWS Kinesis. But for us at the time, Kafka was kind of that right degree of it's boring technology that mostly works and that does what we need it to. So you'll notice, nowhere in there did I say the words event sourcing. Nowhere in there did I say, data lake, data pipeline, right? This was just to address our availability needs first. Because at the end of the day, Honeycomb was designed by a bunch of SREs. Like that's fundamentally the truth, is that our founders were SREs. We cared very much about kind of this decoupling of systems and quick release processes from the beginning. But it turned out to be really, really useful to have this decoupling. Why? Because it turns out we went from having two identical consumers that were doing the indexing of the data after it came out of Kafka, to now we have, I think, 4 or 5 different consumers running 3 different binaries, right? That we're tapping into this event stream of all the data coming in from Honeycomb's clients. And we're now not just doing the processing of the data into our columnar data store. We're also evaluating SLOs on the fly. We're also computing service maps on the fly. We may wind up in the future doing some degree of pre-processing of traces on the fly, right? And this makes it much, much more powerful to be able to say, I already have the data feed. There's an API for accessing it. Just go, right? That we didn't need to configure anything on the producer side to be aware that there are new consumers. They just continue happily writing data, and everything's great. So all of the state now lives in Kafka. Yay! I get to restart everything on demand. I get to replay things in case I mess something up on the consumer side. Great, right? And there's a scary bit. And the scary bit is, if Kafka breaks, everything else breaks. And we do not write Apache Kafka. That is not our area of expertise. So it's much harder to debug and understand what's going on if something in Kafka breaks. What happens if producing sticks? What happens if there's inconsistency between, what happens if you accidentally turn on nclean failover in Kafka, and you accidentally have 2 different Kafka brokers that have a different view of what's on a partition? Ugh, OK. So it turns out that there are benefits that you can pick up the phone and call Confluent or call Avon or call someone else on the phone if you pay them. So there are other people who are qualified to do this, but it still is a factor of that is increasing your time to respond, right? You're not going to achieve 4 nines of availability if there's a 30-minute wait to talk to someone on the phone involved in the debugging process. Here are a couple of other ways that I think are important to highlight about our use case that may not be true of your use cases as streaming users or people who are considering streaming. For instance, we do not use Kafka as a permanent durable data store. We have S3 for that, right? We populate S3 from Kafka, but it's a transient buffer. Typically, at worst, if we lose an indexing node, we'll replay the last hour from Kafka since our last snapshot, right? So we are checkpointing about every hour, which means typically we only have to go back in time about 1 hour. But we do also occasionally need to exercise going through the past day. For instance, if you remember that giant AWS KMS outage in December of 2021, that thing caused us to lag further and further behind because we weren't able to process data. And when everything came back, we had to process and backload the entire past day of data. The other thing is that we don't, right, because we don't do event sourcing, because we kind of have one data set rather than hundreds of data sets, we don't have this problem of schema management. We have one main Kafka topic that everything flows through. And the other thing is that a lot of the Kafka best practices that are written down are like, oh, just let Kafka automatically allocate partitions. You should have thousands of partitions, right? But for the way that we're using it, we expect to have each worker node that is indexing one stream of data be responsible for just that one stream of data. So we're not kind of dynamically allocating hundreds of partitions and migrating that workload among consumer groups between, right? Like we have one indexing node reading one Kafka partition, which means that We have about 100 partitions. You do the math, that means we've got about 200 indexing nodes total running in production. The flip side of this is also that we're pushing Kafka to some of its limits. The designers of Kafka expected you would just horizontally scale up partitions if you needed more message throughput. But we're writing about 50,000 messages per second per partition because we have a finite and small number of partitions. We also do not leverage Kafka's look-back capabilities to run SQL on your previous Kafka stream. We have our own database. That's what we spent one of our innovation tokens on. So we built our own querying language. And the other thing is a lot of people advise you to use librd-kafka, which is a C implementation of the Kafka client. We're just using pure Go. That's a stylistic choice because we are a Go shop, and we prefer to not use CGo. If you're here from Shopify, we owe you a beer. Like, Sarama is really cool stuff, but also it is really hard, and we understand that. So overall, this is kind of what this verbal description is leading up to this architecture diagram. So hopefully you can kind of understand it now, right? Essentially, data comes in, goes into the ingest layer, which we call Shepherd. All of our services at Honeycomb are named after dogs. And then from there, all of that data gets fire-hosed into Kafka. Yes, we have to talk to MySQL to find out, is this customer authorized, which API keys exist. But fundamentally, that millions of events per second is flowing into Kafka. And then we have a variety of consumers, including the SLO processor, but the main indexing worker retriever. And then after that, it gets serialized off to S3, and people can query it. So if Kafka breaks, event ingest from our customers stops. In the worst case, the events drop on the floor. In the best case, the events drop on the floor. In the worst case, right, one of the things that we're most afraid of is if we stop ingesting events, the memory buffers on our clients' applications will start filling up with that telemetry data, right? That's why we view reliability as so critical here. Zooming in even further, right? Like, let's talk about this workflow, right? Like, fundamentally, we have batches of events that come in from customers. Each event is a set of key value pairs. And we wind up not necessarily sending all of the events from one batch into the same partition, right? We can choose to round robin them to various available partitions. For us in production, we operate with n equals 3, right? We believe that durability is important overall. So we want to make sure that we're replicating the data at least 3 times. But for each partition, there's 1 leader and 2 followers. And then for each partition, there's 2 indexing workers that are paired up that are reading that and then writing the data out to S3. So what happens if an indexing worker dies? Great question. Well, as I said earlier, one of the cool things is we snapshot every hour, right? We checkpoint every hour. So when we bring up a new indexing worker, it starts from an hour ago. We tarred up all the state, wrote it to S3, so we just download it back off of S3 and resume replaying from a specific checkpoint, all is well. So where are the places where this goes wrong? How have we seen the system exceed its constraints before? Broadly, it boils down into problems with the producers, problems with consumers, and problems with brokers. And the tricky thing is knowing which one you're dealing with and having the adequate signal to deal with that. So let's talk first about Shepherd, the ingest service, and problems we've seen with kind of the producer side of the equation, right? Your producers do not have a choice about how quickly they receive data. They are getting data and needing to shove it into Kafka. Your consumers, if they get behind, right, they can lag a little bit, they can take some time to catch up, but producers have to process the event or drop it on the floor. So the first technique that we've employed is we do things like automatic scaling, least outstanding requests, so that if one of our worker nodes gets backed up, it lame ducks itself, and then other nodes will take over. The other really important thing is to make sure that you're being economical with how chatty you are to the Kafka brokers. Batch sizing is hugely important for 2 reasons. Number 1, it impacts your compression ratio. Right? You're more likely to see a better compression ratio if you're batching 100 or 1,000 events into one write request to Kafka, compared to if you only write 1 event at a time or 10 events at a time. You're not going to see the same benefits from compression because the compression is at the batch level. The other question you have to ask yourself is, how much data am I willing to lose in case the process crashes? So in our case, right, like we care about not backing up our customers if they, not kind of having memory backup on our customers if we slow down. So we're OK with tolerating if a node suddenly crashes, we might lose a second or two of that customer's data. That's fine. That's why our SLO is 99.99% and not 100%. The other important thing to think about is queue depths, right? There are a lot of buffers involved in the process of writing to Kafka. So making sure that you have adequate telemetry on what the size of those buffers are, what their allocation level is, and how to drain them, right? How to make sure that you're staying within that constraint of how much memory do I have available per producer. Making sure that you have strategies to guard against OOMs, right? To make sure that you would rather lame duck and stop receiving traffic than crash and leave someone's data stranded. The other interesting thing that we've run into is more often than we would like, certainly, one partition will get stuck, right? For whatever reason, the leader for that, the Kafka broker that's leading that partition is not writing data as quickly as we would like. And one of the things that we would like to do is to start determining, like, I should not be writing to partition 5 right now, right? There are other places where I can write that data because I have many partitions available to write each customer's data to. So if I know partition 5 is bad, don't write to it for a couple of seconds. Give it a chance to come back. Similarly, allocating load between partitions, right? We said about 50,000 messages per second is our maximum per partition. It turns out that customers have varying degrees of burst in how much traffic they send, so we need to think about how do we make sure that we are not overwhelming any one partition and routing traffic appropriately. On the broker side, it basically boils down to a question, which I'll get into later, of are you CPU bound, disk bound, network bound, or IOPS bound, right? Those are typically the 4 things that you tend to see. So if you're CPU bound and you previously were using storage class instances, my advice to you is the i3 generation of AWS instances are hilariously underpowered on CPU these days, right? They're using CPUs built in 2014, 2015. Do not use the i3 generation anymore. There's the i4 generation, and yes, I happen to like the ARM-based Graviton instances, but there are also Intel-based i4 Intel i4i instances that also will work, that are much beefier on CPU. So for that, look at your CPU graphs. On disk storage, for a very long time, we were storage bound, right? We had these massive amounts of data because we were saying, I want to keep 24 to 48 hours of data just in case, as a safety blanket, in case I have an outage I need to replay. But we found a couple of things. Number one, that we had machines that were just sitting there idle, doing nothing, except for having data on their disks. And that was not super economical. So we decided we wanted to pare back on that. But it turns out that if you have a smaller hot set, you can keep that smaller hot set on local NVMe and then tier the older stuff to S3 or some other longer-term data store. And fortunately, we tried doing it ourselves. We tried using a write-back cache and using LVM. That did not work well. The tail latency really shot up. You might be tempted to say, OK, that's fine. Why use instance stores, right? Why not just use EBS? And in fact, it's actually very strange. Confluent themselves recommend using EBS volumes for backing your Kafka clusters. I do not understand this because it is both very expensive and also the latency is worse than using local NVMe storage. And when you're producing, especially when you're focused on the time to respond to the client by saying, I got this, you can drop it from your memory, the faster the local NVMe SSD, the faster you can get the commit acknowledged, the faster you can respond to your client and done. Other things to look at in terms of brokers, auto-balancing the load, right? If you've got vastly disparate workloads on your brokers, that's the first place where if you're exceeding capacity on one broker, load shed. And finally, horizontal scale out as needed. This is one of those things where you don't necessarily want to be adding and removing Kafka brokers from your cluster all the time, so you kind of have to scale for the maximum that you'll see during a day or week. So we kind of recommend trying everything else first before you horizontally scale out. On the per consumer side, some of the pain points that we've seen have been the weirdest here. So for some reason, at least with the Sarama Go library, if you have a consumer talking to a broker, even if it's consuming 5 or 6 different partitions, we find that if you have 2 or 3 busy partitions assigned to the same, that happen to live on the same broker, that happen to be assigned to the same consumer, that those will contend with each other. And those would be fine if they were assigned to another broker or if they were being read by a different consumer, but it's kind of that problem of there is only typically one connection from each consumer to each broker for which the connections for each partition are multiplexed. So if you run into this, run more brokers, or just, if you have 100 partitions, run 100 consumers. It's probably fine. This is another really, really counterintuitive thing. Everyone, including ourselves, have said, right, like rolling restarts are great, right? Like you should do percentage-based deploys. You should not restart the whole world at once. This falls down when it comes to streaming services and consumer groups. Because consumer groups try to automatically balance the partitions that they're reading between the available nodes, which is that if you restart one node, it'll reassign everything, cause things to get back up, and they'll have to replay. And then you restart another node, and then that same work happens again, and it happens again, and it happens again. So you're incurring, for 100 different consumers, you're incurring 100 disruptions to update those 100 tasks. It is a lot better to just stop the world and start the world when you're doing your deploys. So this is actually a option in Kubernetes that you can use to say, I want to just tear down everything and restart it rather than do rolling deploys. But the number one thing that you can do to make your recoveries faster is, for our data storage service, yes, we have to, if we lose a node, replay the past hour. But if you can checkpoint to local disk and assume that you can keep your local disk between restarts of your services, it will dramatically speed up the rate at which you can recover if you're not doing a complete cold start. So once you've kind of identified how to tell, is it a broker problem, a consumer problem, or a producer problem, and kind of address those things, here's some further kind of 201 level optimizations to consider that will help you get the most of your cluster and help you ensure that you don't have to throw more hardware at the problem. So the first question that I ask you is, do you really have to run the brokers yourself, right? Google Cloud PubSub exists. Amazon Kinesis exists. Confluent Cloud exists. Our friends at Intercom love to say, run less software. Is it business critical for you to run this software? And for us, we determined, yes, it was business critical for us to run this software, and we wanted to hire someone like Terra onto our team who could help us do it, right? Because if, yes, being able to debug things within 5 minutes because you have the expertise in the team, that's really, really helpful, right? That decreases your time to resolve. If you have a weird and hairy case, you might need to call up Confluent and get support from them, and that might take 30 minutes, but a majority of your outages will not be that 30-minute case. But if you are outsourcing that, right, and you're having to talk, if for any problem with your cluster, you have to talk to Amazon or Google Cloud or Confluent, that really raises your time to detect and time to respond. And given our availability requirements, it just made sense for us to continue to keep that in-house. We did think about it, but at the end of the day, the thing that Ben said rang true. Kafka's the beating heart of Honeycomb. Outsourcing it just wouldn't have made sense. Another really important optimization. Use Z-standard compression. If you are still using Snappy for your Kafka replication in this day and age, you really shouldn't be unless your consumers and producers are really CPU strapped. But in general, throwing CPU at it is a lot cheaper than paying your favorite cloud provider cross-availability zone transfer fees. Because you are running your Kafka clusters across multiple availability zones, right? Right? If you're not, AZ goes down, and you can't rebuild your clusters. That's no good. So we find that it's about a 10%, 20% CPU hit for the Kafka-specific part of the workload, not overall across all of our workers, but delivers about 20% bandwidth savings, so highly, highly recommended. Speaking of DTAZ, fully utilize Kafka's replication, right? Why are you paying to write to a Kafka leader, have the Kafka leader replicate it to 2 other availability zones to make sure you have cross-availability zone replication, and then you're always, from your consumers, reading it from the leader? You've already paid to replicate it into each availability zone that you're in, or at least 3 availability zones. Why are you always going to the one availability zone that might be out of AZ for you? No. Kafka has a feature called follower fetch. Follower fetch is super, super powerful, and I believe that Pulsar does the same thing, right? Like, basically, reading from your followers, even if it's, maybe a second or two stale, that's going to save you a lot of money. And yes, of course, if you're more than 5 or 10 seconds stale, go and read from the leader, but that's going to be much, much rarer. The other thing that was the source of my grump earlier about using EBS or using Google Cloud Disk, persistent disk, is Kafka already is providing that durability factor of R=3, right? You should be able to lose any availability zone, any machine, and be able to replay and recreate the data. Why are you paying your cloud provider to redundantly store the bytes on that disk of the Kafka log? That just does not make sense to me. You know that it's disposable data that you can recreate, so just keep the data on local NVMe. Don't pay separately to have higher latency and higher cost. And use the most efficient base hardware. But be careful of unknown unknowns, right? Be aware of what the dimensions of broker saturation are. And also be aware that your cloud provider may not hard throttle you when you hit the limits. They might make you believe everything is fine for 3 or 4 hours, and then you're in a metastable state where you get out of the metastable happiness, and suddenly you can no longer recover. So in that vein, I'm going to use my remaining 15 minutes with you to tell you about kind of how we found our way to a trim, lean, and efficient Kafka cluster. So we originally were running something like 30 or 40 i3EN class Kafka nodes, and we were using them only for the on-disk storage, right, to store that 24 to 48 hours of data. And we decided, hey, this Graviton thing is efficient and new, and hey, maybe we can use EBS to decouple the amount of disk storage from the amount of CPU. So we tried that, and then first we bumped into network saturation limits, and then we bumped into IOPS limits, and then we wound up having machines hang and not come back because of bugs in the underlying hypervisor. I kid you not. We found a hypervisor bug by exercising it with our workload. Scary stuff. So basically, each time you run into one of these limits, you have to be able to figure out which limit is it, what do I need to scale up, or even better, this was a system optimization, right? This was not our cluster was imminently in danger or on fire. So we decided burning out our people is just not worth it, that we'd rather pause the experiment, go to a safer configuration. So we actually kept the same storage class nodes, but we just said, we're going to run fewer instances and tier the data off to S3. And that's how we'll get our cost savings. We don't have to optimize all of the dimensions at once. So we did the change one step at a time. First changing to using tiered storage, and then changing the worker nodes once we actually had a one-for-one replacement of i3 with IM4GN. So that's what we did. We successfully migrated to running many, many fewer nodes, right, going from 30 to 6. And then after that, we replaced the 6 Intel nodes with the 6 Graviton nodes. And finally, then, we hit the point of the system is trim and lean, but we're running into capacity limits all across the board, all at the same time. That is a sign to us that we need to finally horizontally scale the cluster because of organic demand rather than because our system is poorly optimized. But on that note, the other thing is you shouldn't just be playing with hardware if you're pushing the limits of your system. Often, software problems can mask the underlying performance of the hardware. So profile. For systems like Kafka that are essentially a black box that you cannot necessarily understand intuitively, getting CPU profiles enables you to, even without a deep understanding of the source code, see where am I spending the majority of my time. And that enabled us to make adjustments based off of that, like using a better JVM that had better garbage collection characteristics, knowing which Java native C libraries to update or recompile. And in particular, we found that with tiered storage, it was saving us a lot of money on local disk storage, but we're spending a lot of CPU time computing MD5 hashes. Oops. So basically, getting profiling data in flame graphs like this helped us identify, is the workload spending time where I expect it to be, or is there something that I should be optimizing away? The other thing that we view as really important to discovering the limits of what we can do is not just testing the system at happy state, but actually actively stressing the system once a week. In fact, it's just past 11 a.m., so you can come see me at the Honeycomb booth afterwards, where I can show you that there is currently, right now as we speak, a live Kafka broker migration happening. Every week, we replace one of each consumer. We replace, run AWS terminate node on a consumer and on a broker, because an end-tested backup is not a restore. And in particular, it takes additional bandwidth and CPU and so forth out of the system, both from losing a node, as well as the effort to replay and recreate that node if you need to. So we've found that it's best to, during peak hours, right, during the peak of our traffic, verify we can safely lose a node and replace it without the system falling over. And we do that every week. And that enables us to really make sure that we know about the uncharted territory by charting it before we actually run into it in production. Otherwise, you might go months between broker failures, and you might discover, uh-oh, our system was metastable and we can no longer recover. In streaming, the data does not stop. So the more headroom and slack capacity you have in your system, the more time you have before things go pear-shaped. And that means that you don't have to treat, oh my God, like Kafka slightly degraded as I need to run to my computer, like, it doesn't matter where I am or what I'm doing. And instead, you can kind of take your time to solve the issues. So now, Kafka later goes away, and it gets replaced automatically, and everything is happy, right? But how do we know for sure? The answer to how we know for sure is we keep primarily application-level observability. That's what we drive our SLOs on, right? So we have trace spans per consumer that report how am I doing every minute and what work did I kick off based off of the spans I consumed. And we also do some very, very, very heavily sampled produce requests. We create trace spans for each produce request, but it's very heavily sampled because it turns out your observability cannot be 100% the size of the system itself, or that would be very, very expensive. And the way that we correlate those things is there's always a link back between a record of something that you consumed off of the queue, off of the message queue, and where it was inserted into the system, so you can go back and trace the lineage of your data and where did it come from, how long was the delay between when it was inserted and when I read it. At the system level, unfortunately for now, what we're primarily relying on is not traces but metrics. So messages per second, CPU, under-replicated partition count, disk, things like that. And then there are a couple of more advanced things. So I did want to briefly show you on the consumer side, right, this is the latency, the maximum latency that we've seen over the past minute at a time, right? I think the resolution on that is minutes. And you can see every hour on the hour we do a deploy. And then because we restart the world all at once for that consumer, the latency spikes up to maybe like 60 seconds or 2 minutes, and then it all comes down immediately at once, rather than kind of having a staggered rolling impact where nothing ever catches up before it's perturbed again. So similarly, this is exemplifying what I was telling you about kind of creating a minutely tick, basically saying, hey, the consumer is still running. Here's the work that I did. Here's a snapshot of what I did. So you don't have traces that go on hours and hours and hours. Because, again, it's not request response. The workload never stops. And this is what our Kafka dashboard looks like, right? Basically showing what's my CPU, how many messages per second am I getting, have I had a change in the Kafka coordinator. So these things just help us make sure that if there is a blip that is observable from the producer or consumer, that we can correlate that pain to Kafka itself. We don't normally look at this dashboard, right? It's not like we kind of have a Starfleet where we're just always having that on screen, but it's helpful to orient and know where we are. So SLOs. There are no SLOs on Kafka itself, right? What we care about is the user journey. Kafka's the how, not the why. So we measure, can users shovel data into Honeycomb as quickly as possible? Is there adequate freshness? That's what matters to our customers, not how many under-replicated partitions does Kafka have. So what's our future work? What are we intending to do next? I think the primary thing that we want to do is we want to make sure that as we grow and scale, that Kafka does not produce toil. Kafka is the beating heart of the system, but just as you don't think about your heartbeat every single second, we shouldn't have to think about that either, right? So we need to make sure that as we add new clients, that we're not creating subtle imbalances in the system that require human intervention to solve. This does not mean that we need to go to Kubernetes. Our problems would not be solved by putting Kafka on Kubernetes. And in fact, putting Kafka on Kubernetes would make our problems a lot worse, I think, right? More frequent restarts. We're already restarting once a week. Kind of more layers between us and the bare metal. a Kafka broker to us consumes the entire bare metal machine or the entire virtualized machine. We don't need more layers of abstraction. We need fewer. We just need better management and healing and self-control. So if you're interested in any of what I said, if you'd like to learn more, if you'd like to see our currently running terminate instance and watch it recover, can stop by our booth. There's also some further resources at Honeycomb's website. And also, there's a copy of my book. Feel free to get a copy for free right now, where we talk about kind of how we leverage Kafka as part of, right? Like I didn't tell you about the data persistence and storage. What happens with our consumers after they consume the data from Kafka? This was only focused on the streaming. So that's what I have to share with you. Thank you very much. I hope you found it educational.
Let's give a